and then this will be left over in pathway 11.
Okay,
So
so for start fast. Right now it's 12:50. Just a quick announcement before we have our guest lecture or Christine here to start the lecture. +2 for this week's lab goes to groups A, C, and E. So keep up the good work. Yeah.
Okay, thanks. So let me know if something isn't clear, or you can always reach me at my email or my you can always text me or something or call me. The two things that you need to remember for perhaps a quiz is spectroscopy is a secondary method. A primary method is something like vacuum oven, where, you know, like you put in the sample, you weigh the sample, you get a difference in weight. That difference in weight is moisture. That's a primary method. And so then if you see a spectral difference that's associated with that difference in that primary method value, then you can build spectroscopy as a spectroscopy method, as a quantitative method, because it's really convenient. It's fast. It can measure multiple things at the same time. So like for example, in milk, you can measure the protein, the fat, the lactose concentration, all in one spectral image. Takes seconds. You're seeing more and more spectroscopy systems in line. So you can do that for like oil quality, all sorts of things, flour quality. We use it for flour quality, for our oat flour, to make sure that it's good enough to go into our Cheerios, for example, at General Mills. So although you can see a lot of precision in a spectral method, you'll never have more accuracy in a spectral method than the accuracy of your primary method. So whenever you're plotting this in a quantitative way, primary method goes on the x-axis, whatever peak height you're measuring for your spectroscopy on the y-axis, and that's how you create your correlation curve if you're doing a simple linear regression. Okay, so now I've got a boatload of slides. I could talk about this for weeks, days, years. The slides are there for you to look through, because this is an emerging method that we're seeing more and more use, especially as what happened more recently, like around the millennia, when the millennia came around, we saw a lot more power in computing. Computers got faster, we could get more data, we could crunch bigger data because we could manage data in clouds. So things went beyond, as I'm sure you see, beyond simple linear regressions now to multiple linear regressions, partial component analysis, and even to bigger AI type approaches of handling data, which is, you know, like random forest, other type cloud things, or map pretreatments, maybe taking a derivative of the data. So all of those are great ways to quantify. When you get to more and more complex math, that's when it gets harder and harder to make sure that you're seeing the truth, as opposed to maybe the math is getting ahead of you. So there are ways to do that, and the process in general is called chemometrics. But I'm sure some of you folks will be in a lab someday doing this. Some of you won't. Some of you will be a developer, or you'll be a manager. So you just want to make sure you ask the right questions so that that data makes sense. So you're not modeling data that takes you down the wrong path. Always give it a sanity check, okay? The other weird thing about spectroscopy is that when you're using spectroscopy in the qualitative sense, like, do I have a protein? Do I have a fat? That's when you look at the peaks, at the main peaks, and you do your spectral interpretation, which that qualitative information is really powerful. That can also be part of your gut check. It can help you see the difference between really complex systems. If I want to know, is this yogurt got the right fatty acid profile versus that yogurt, I could probably just do the spectra of both of those and subtract the spectrum. And whatever the difference is, then I can look at those peaks. So when you look at qualitative spectra, you look at the big peaks. When you look at quantitative spectra, you may not be looking at the big peaks. You might be looking at some different peaks that might look like little peaks, but mathematically they might be important. The other thing about using spectroscopy in a quantitative way, you need a lot more data, right? So qualitatively, I can look at one spectra, maybe 5 spectra. But if I'm doing this in a quantitative space, depending on how complicated my question is, I may need to have thousands of data, thousands of spectra, which might not be a problem if it's automated, or I use an approach called Fourier transform. So if you have just a regular kind of spectrometer with a light source and a slitter, and then, what's being reflected, that's one spectrum. And that can tell me a lot. But if I need quantitative data, I need to take 10,000 spectra, do mathematical transformation of that data, and then that is what actually gets quantified. The best way to think about the difference between Fourier transform and a dispersive unit is, has anyone seen a vinyl record? Okay, great. Vinyl records, you play them, they're great, they've got rich tone, but they also can have scratches or skips, and they age. But who else has seen a CD? Okay. So for every song, the CD actually is the Fourier transform of that vinyl record. So now you will still you'll recognize the song. Some people who are real audiophiles say that the sound isn't as warm. It's a little different. There is some mathematical compression, but you don't have any skips, you don't have any pops, you don't have any hisses. So there's a lot more data on that CD than that vinyl record. You can still get the same amount of information qualitatively, but quantitatively, mathematically, very different spaces. Okay? So that's my little lecture about spectroscopy that I think you need to know. Now I've got 40 slides to plow through. So welcome to Friday afternoon. So sorry, I'm apologizing in advance. Okay. Hopefully my slides will advance. Nope. Maybe I can do it this way. There. Okay. All right. Where are we talking spectrally? Okay, so all in the electromagnetic spectrum have been used to quantify and characterize molecules, electrons, atoms of some sort. So I'm going to focus right about here in the near IR, mid IR, and far IR, although I'm probably not. I'm mostly going to talk about these two. Other thing I want to talk about is hyperspectral imaging, which is really emerging. And it's really only been able to take hold because of that cloud, the AI system. Because when you've got all the spectral information getting collected all at the same time, the data that you get in one image is massive. So you need to have some really high-powered math in order to handle it in a quantitative space. In fact, qualitatively, hyperspectral to me is super useful. If I want to do some qualitative characterization of something, I'm going to stick with the classics, IR or Raman. So these are the movements that you're going to be looking at these different energies. So we're focusing mostly on vibrational and rotational energies. So vibration is, of course, how a molecule is moving, right? It's fluctuating. But rotation, so a molecule could either be doing this, or this, or this. So, or it could be twisting, which is the rotational, right? All of those movements have different energy signals. And that's where you get a difference in signal or a fingerprint of a molecule. Okay. So I want to also talk about Raman because Raman is like the anti-picture of IR. If something is IR active, it generally is not Raman active, and the reverse is true. So if you've got long polymers that you're not getting a very good IR signal, the first thing you should be saying to yourself is, can I get a hold of a Raman? Because then you'll get a lot of information. So, spectroscopy, you've got the dispersive, which was, like I said, the vinyl record. You've got reflectance and transmittance, which are slightly different ways to see the data. Then there's the Fourier transform, which is that CD version of it. You've got qualitative and quantitative, and this is the spectral range that we're talking. Okay, mid to. What can we use it for? Qualitative, as I said, identification, adulteration, compositional analysis, again, like I said, a secondary method. Quantification, a lot of quality assurance. The nice thing about this is that not only could you put a probe in line, but you could also use this sometimes like a pharmaceutical pill manufacturers will actually shoot a beam through the packaging to make sure that a drug has not been adulterated or, it's containing the right amount of active compound. So, okay. So here are some spectral comparisons. The other nice thing about these spectrometers is they have libraries. You don't necessarily have to build your own, but especially if you're trying to identify things, the Georgia Forensic Library is probably the best one because they have the oldest library and they've just got published pure spectra that you can compare your samples to. So what I've done is whenever I've had an unknown sample, say I get an ingredient from a supplier and I'm not really sure that it's what they say it is. I can run the spectra and then I can run it against the libraries and then it can tell me, oh, this might be contaminated with maltodextrin or it's been, contaminated with starch and I didn't really want to pay for starch. I wanted to pay for my expensive ingredient. So the Georgia Crime Lab and the Forensics Lab, best libraries around. If you don't buy a library, then you can build your own, where you go and buy like Sigma Aldrich pure chemical compounds, run the spectra, save it, and then that's your own library. Many times, the valuable thing about these spectra are the libraries. So whenever you're buying a new system, say I've got one vendor, a Buki, and I want to, buy a FOSS because it's cheaper or it's got something better, that library is not transferable. So you have to think about that too. So the other thing that's important about a spectrometer is the optics. Although optics have come a long way these days, so usually cheap instruments have cheap optics. It's kind of like your phone. If you get a good phone, you're going to take a good picture. If you get a cracked phone, you can have a cracked picture. So these are some of the things that I thought these spectra. So if you can see here in the mid-IR, you can see some differences between this top band is ascorbic acid solution. This is the one below it in blue is a citric acid solution, and then sucrose, and then here is just a juice. So in this example, they were looking at what's the composition of this juice, and they're comparing it to their library of sucrose, citric acid, and ascorbic acid. So you can see that the patterns are a little different, but they're also a little same. So you can see here with this dip down between 4,000 and 3,000 wave numbers, that juice probably has maybe some combination of sucrose, citric acid, and ascorbic acid. When you start coming over to about closer to 2,000 wave numbers, you can see that, well, again, you've got a lot of activity, but it's probably more sucrose and citric acid. So then that's just how you do that. You just kind of look through your bands to see where's the activity. And again, a computer can do that. In Raman, you kind of can see the same thing. So in this Raman example, you can see sucrose in green, lactose, which is pretty similar, but not exactly similar. And what's interesting about this spectra is that you see how spiky the sucrose is and how round the lactose is. That also gives you an indication of how crystalline something is. So this lactose is more of a powder than this sucrose. The spikier it is, the more crystalline it is. If this was a powdered sugar, it would look a little closer to the lactose. So then you can also see how you've got skim milk powder, which is going to have a lot of lactose in it. Whole milk powder, which does have some lactose, but it also has, fatty acids in it. Whey protein, cocoa butter. So in this case, I wouldn't probably use this bandwidth. So this is where I talk about quantifying versus qualifying things. If you look at the wave numbers, the Raman ship, like just after 2800, you can see that they're all kind of spiky here. So would I use that area, that frequency to really see the difference between whey protein and lactose? I probably wouldn't, because there's just too much overlap. I might actually look over here, over at between 32 and 3600, because there are peaks. There's hardly any change in the baseline there. There is a broad peak. So I might actually use that section of the spectra to tell the difference between the two, even though that's not the main peak of the spectrum. So those are some of the things that you start looking at when you look at spectra. There's also a lot of other differences, and that's where what a computer will do is it will actually highlight the windows of best characterization and best quantification windows. So, any questions so far? Okay. Okay, so it's non-invasive. Like I said, you can shoot it through packaging sometimes. It's rapid. It is super fast. Requires minimal or no sample preparation. It kind of depends. If you want to do a transmission, then you actually do have to take your sample, grind it into a powder, mix it with KBr, potassium bromide, squeeze it down into a little crystal window, and then you can do a dispersive IR that way. It is suitable for routine analysis, and it is, what I like about it is because it's non-destructive, you can do spectroscopy on something and then use your sample for something else. So if you want to do your primary method, you do your spectroscopy first and then send it off for primary method. Or if you want to just do a quick QC check in a lab, then you can just take a sample and then put it back into your regular stream of making whatever. So, but if you do that, you have to make sure that you regularly calibrate and check the calibration on your spectrometer. So you'll always want to be doing routine test analysis between, just a test to make sure that your primary method agrees with your secondary method. Sometimes what I always have to do every year is there's a new crop year. So oats are always a little different. And even though the beta glucan might be the same, it might be deposited differently in the grain. So sometimes beta glucan is like really concentrated in between the cells close to the starch. Sometimes it's a little more diffuse closer to the bran. And where that beta glucan is and a little bit of what's the average molecular weight of that beta glucan can shift the signal a little bit. So every time there's a new crop year, I have to be recalibrating that spectrometer and comparing it to primary method. And then sometimes it's usually just little adjustments here or there. Maybe just the window moves a number or two, but it's enough to be important to do. So, okay. Energy absorbed is infrared, energy scattered is Raman. You can many times, if you've got a really nice bench system that uses a laser, you can use the same light source to do IR as well as Raman. The really cheap systems don't use high energy lasers. They can only do IR. Usually if they can do near IR, they have to use a laser because near IR requires a lot more energy. So usually you can get a bench that can do IR, a bit into the near IR range and Raman. But those are the really nice analytical benches. If you're talking about QC lab or stuff that you stick on a tractor or things that you put on a drone to fly over fields, those are probably cheaper light sources. So won't be doing Raman. The other problem with Raman is you have to really jack up the energy because what you're measuring in Raman is tiny compared to what you can get in IR. And I have burst samples into flames with my Raman. Just so you know. So when we're talking about IR, we're talking about when we're going up from this little first short little purple bar or arrow. We're going from the ground state, we're shooting energy at it, and then as the molecules absorb the energy, they start moving around, and then they'll go up to a higher energy level. Depending on how they absorb that energy, that's going to give the spectral fingerprint, right? When it comes to Raman, we actually have to really jack up the energy, which is why we need to have the powerful lasers, right? And then what can happen is we're going to excite those molecules, and then they're going to relax. Now, sometimes they relax right down to just the normal energy state, which nothing there, right? But sometimes, not often, but sometimes it'll actually go and it'll stop at a vibrational or a higher energy state. It'll get stuck. That is what you're measuring. So it's not every event. That's why you need so much energy, and the signals in Raman are significantly smaller. But like I said, it will show you things that you can't see in IR. Okay, we talked about small energy differences, complementary, and then of course, this is really about energy of the system, Planck's constant, and then frequency. So this is just the basic equation. That's the same equation that you would see for UV vis and for anything else when you're doing analysis. And I mean, I love the instruments. I love taking them apart. But if that's not your jam, all you really need to know is make sure that you understand the primary method, the secondary method, everything checks out, math. And then qualitatively, you can learn a lot. We have our own spectroscopists at our lab. So I just rely on those guys. So what's the other difference between, so wave number is the inverse of wavelength. So you can just convert between these two. Some people like to say wave numbers, some people like to say wavelength in centimeters. So just make sure you know your units. And then the other thing is, what about transmission versus absorbance? It's really just your preference, what you like, because they're just inverses of each other. So what's transmitted, what goes through versus what's absorbed. So if you have low transmittance, you're going to have high absorbance. So this is actually an image of people are using spectroscopy to understand the origins of like pigments in art so that they can actually more accurately date the art, as opposed to like, there was like carbon dating and stuff like that. So now you can actually tell, is this truly a Picasso, because is it actually using Picasso's pigments? So they're using a lot of spectroscopy, again, fast, and it doesn't destroy anything. So you don't have to take out little paint chips anymore like they used to. So those are the differences of that. And then I'm talking a little bit about what vibrations were around like that. So we've got some stretching, we've got symmetric ones where both molecules are moving, asymmetric. So any way, actually, you can move your body. Molecules pretty much move, except if they're in a giant conga line connected to other molecules. So, but as they're moving, there's a tension because, you know, there's going to be an optimal distance for that electron cloud to stretch, right? So if you've got, you know, an oxygen and a hydrogen, as it's moving around, you're shifting around that electron cloud, you're putting a little more tension on that. It's just like a spring. It'll want to come back to its lowest energy state if it can. So all of these things are what is creating those peaks, all these movements. Okay. And I think those are, I'm not sure if that's a duplicate slide. Anyways, I wanted to talk about this one. Raman versus infrared. So infrared is the absorption of vibrating molecules. Active peaks if there is a change in the dipole moment. Okay, so that's about the electron cloud. And are you shifting the polarity of that cloud? Then it should be IR active. So if you've got, so in this case, if you've got these two molecules and they're in line and they're doing this, they're not really changing the dipole of that. They may be stretching it, but there's no change. So if there's no change in the dipole moment, then it will be Raman active. Okay, so scattered light of vibrating molecules, it must not have a dipole moment. Active peaks if there is a change in polarizability. So how it's going to shift that light, how it's going to interact with the light. So symmetrical, Raman active. Asymmetrical, IR active. In plane and out of plane bending, again, if there's a change in the dipole moment, IR active, right? Because it's doing this. So if you look at me like this on the side, I am changing. If these are positive and my body's negative, I am changing the dipole moment, right? So usually polar things are more active than nonpolar things. Nonpolar things tend to be more Raman active. So okay, so this, I am sure if you had organic chemistry, you probably did some spectral interpretation. I like to do spectral interpretation. Actually, I thought it was fun. And I get to learn a lot this way. So here is a spectra of butyraldehyde, and you can see, you know, here's your CH stretch. So your CH double bond O stretch. So now your electrons running around a little bit differently and stretching. And then this is your carbonyl stretch. So if you know kind of what you're looking at, you should be able to do the spectral interpretation. Sometimes there's overlap in these bands, so that if this was contaminated with maybe maybe a nitrogen group, like a very similar compound, but it had a nitrogen group somewhere, you might see an extra peak, but it might look like this, and that's where it gets kind of confusing when you're doing spectral interpretation. So again, libraries are your friends. And in fact, there are books and books of libraries published, but there's also a lot of electronic libraries, so that you can even just look online and find the spectrum. In fact, I grabbed this from, Google. The nice thing, if you're going to be using spectroscopy for qualitative analysis, not quantitative, but qualitative, it's nice to have this table handy so that you know, okay, well, alkanes are going to be active in this area, the 3000 to 2800 wave numbers. And then the amines. So this is where it gets kind of confusing. So amines are also active around 35 to 3300. You can see how that might be kind of close. So I always like to have this. Usually a spectroscopy lab will have this actually pasted on a wall somewhere just because it's handy. But otherwise, again, computers will do that for you these days. But it is nice if you're the person, not the spectroscopist, but if you're looking over the shoulder of the spectroscopist, it's nice to have these numbers in your head so that you can say, oh, wow, that's a really big carbonyl peak. Is this, is this an amino acid? Is this a fatty acid? What is this? So, so that's what's kind of handy. Otherwise, honestly, the last time I used this in great detail was when I was in school. So just have it posted somewhere if you want to. So IR radiation, can it be employed for mineral analysis or not? How about this? What's KBr? Potassium bromide. So if I want an IR spectra, I usually take my powder, mix it up with potassium bromide, squeeze it into a crystal, and then I put it into my IR machine. So the answer is KBr will be invisible in that case. Everything that I showed you on that table before, none of those were ionic bonds. It's all covalent, it's all organic. So probably for minerals, like just minerals, like sodium chloride or something like that, I wouldn't use spectroscopy at all. I would use something else. You could use atomic absorption, you could use ICP, plasma type stuff. But if I'm going to be using Raman IR, something like that, that's usually, I'm talking organic. It could be an alkyl halide because that just shifts those bands, those covalent bonds. But if it's just a salt, I wouldn't use this spectral technique for salts, for example. Okay, so here's a little bit about dispersive instruments. So you can use nichrome wires with a ceramic core. These are those, this would be like a handheld little IR, or if you're doing like QC on a plant floor, you would have something like this where you've got some simpler detectors, simple electronics. It might be wired to, actually I was just seeing that Buki has a handheld IR that has the lower quality energy, so lower energy light source. Usually has a monochromator, which is just slits that will allow certain wavelengths to come through. And then a simpler detector. Those can be hooked up electronically now to the bigger benches that have big Michelson interferometers, which are the Fourier transform systems. So these types of mid-IRs are really similar to your UV-Vis spectrometer. If you've ever had one of those like Beckman UV-Vis things where you just stick your test tube in there, that's what these are. So you can get some really affordable mid-IR. Usually what you're sacrificing here is the precision of detection. So your wave number or your wavelength windows might be plus or minus 5 instead of plus or minus 2 or 0.2. So again, you're kind of sacrificing that accuracy and precision just because of the optics and the electronics. Okay, so a dispersive system, I like dispersive ones if you really want to get a nice fine fingerprint out of something. So that's where if I'm going to have my pure compound, I've made my KBr pellet, I'm going to stick it in there. So I'm going to stick my sample in here, got my source. It could be something as simple as that nichrome wire, but it could also be like a lower energy laser. And then I'm just going to shoot it through and then whatever the detector sees. So that's really, if I want to really understand like I get a little better refinement on if I want to understand how crystallized something is or what kind of crystal it is. So we know that fats have different crystal morphologies, right? You can start to see some different crystal morphologies using this dispersive type method. Again, I probably would use X-ray for that if I want to actually do some really hardcore crystal shape stuff. But this is because these are usually really affordable, small thing, footprint. Like we don't have an X-ray spectrometer in our lab because it would take a lot of energy and you have to have special training for it. This is something that you don't need to have special like safety training, and it's pretty rugged and pretty affordable. So you can get a lot of information right there. Okay, mid-range Fourier transform. So again, we're using the Fourier transform so you can get a lot of information. You can run within a few seconds, you can get 10,000 spectra instead of just one. And so now you can start quantifying. So what the interferometer does is it's constantly moving. So you've got this beam splitter. So here's your light source, which is the little sun thing up here. And then it's shooting down to this mirror that's on a 45-degree angle. And then there's a flat mirror and another flat mirror. And so this mirror is constantly moving. And so what that does is that's what kind of breaks up the spectra right there. And so then it'll just keep getting the information. And what it will do is, I think my next slide is about the Fourier transform. So what you're going to do is you've got your light source and your sample, and that mirror is moving. This, if you actually see the raw data, if you're actually going to run your own spectrometer, you're going to see something like this. You're going to say, okay, that looks like a big fudge. And then my sample looks like this. And you're like, well, okay, I can see that it's a little different over here, but like, what am I going to do about this giant smudgy thing? And so this is what happens is they will subtract the background out of the sample, and then you will get your spectra. Like here it is in absorbance, and here it is in transmittance, which is just the inference of the two. And so now you can actually see, okay, this peak is this peak. That little doublet is this doublet here. And then these three peaks are these three peaks. So this allows you to improve your signal to noise ratio. So if you've got things that are really at low concentration, you'll be able to pick it up through Fourier transform. You might not be able to pick it up necessarily through a dispersive gamma. There's a couple other things I wanted to talk about. So we've got transmission, where you could use it with pellets of potassium bromide, or you could throw it in a very pure mineral oil. So remember, IR spectroscopy can't see long polymers, so it can't see neutral oil. So mineral oil is pretty IR inactive. So again, if you've got something, you could maybe disperse it in the oil. The thing you can't use is so cell windows you can use are made of non-absorbing material. So you can use zinc solenoid, sulfide salt, but you can't use something like glass, silica glass, that will actually interfere with your IR spectra, and you can't use a quartz cuvette. So you have to use something special. When you've got Raman, you can use a quartz cuvette or glass. That's okay. So there's also another way to look at it is attenuated total reflectance. And I don't think I have a picture of this, but if you have like a paste, I did ATR on corn syrups. And so if you actually have the incident light coming in at an angle, so say you've got a slide and you smear on top of it your corn syrup. Now you've got a thin layer of corn syrup on top of your slide. If you actually aim your laser on an angle, it will actually start to bounce up and down. And I would use I think I used a gold slide for this. And it would bounce up and down, and how it actually hits and it's bouncing will give you another bit of energy. You'll actually get more spectra out of it if you run it in ATR. Sometimes that's a little more convenient than, oh, I'm gonna do it in transmission. I need to try and grind it into KVR. I've broken so many KVR pellets, and then you have to start all over again. That just drove me insane. But total ATR, you can just put it on something, stick it on your instrument, and then it'll do. So that's a lot easier. And then there's some internal reflectance cells, which is kind of a rip off of the attenuated total reflectance. But those are special benches that spectrometers in spectroscopy labs will actually use, as opposed to your QC. So some other things you can do is you can hybridize and connect these with GC. You could do a GC FTIR. Otherwise a GC, you know, what they've got flame ionized detection, they might have a mass spec or something like that. So you can connect a gas chromatography system with an FTIR. You can also use a microscope and connect that. So that's what this bench is you've got a microscope, and then this is the IR bench. So what you can do is you can actually be looking at your, I don't know, it could be even maybe it's a cell or something like that. Maybe you're in a dairy lab, or you're checking the sourdough in your bread. So you can take a slide like you normally would do with a microscope, and not only do you have the light looking through it, and you can take pictures of your sample, but now you can actually shoot a beam, your laser beam through it, and now you can get the spectral imprint of what you're actually looking at. So maybe if you want to see, ooh, what's the lactose concentration in my sourdough starter? You can not only see like, oh, okay, the microbes are growing. Oh, and there's a lot of lactose, or, oh, no, there's not a lot of lactose, or something like that. So you can get a lot of different information if you start hybridizing these systems. Okay, so I think I have 5 more minutes. Oh, let's see. Calibrations. We just need to know that so one thing that I really like IR milk, I think a few years ago there was actually a competition. So what you can do with some of these new IR milk analyzers is, like I said, you can analyze for fat, protein, and lactose all at the same time. But in order to do that, you need to make sure that you're calibrated. And you need to have a nice, robust calibration. You generally never want to extrapolate. You always want to interpolate within a calibration. So if you think that your samples are going to be between, 2% fat and 20% fat, then you should be running a standardized calibration curve within that area. If your concentration reads after you've done the chemometrics or the quantification, if it reads like, 22% or 25%, that's out of your calibration range, and you either need to get a new set of standards to calibrate up higher, or you need to do something else. So, but that spectral method will not be able to extrapolate and still be quantitatively valid, because it's always dependent on the primary method. Okay, so we've got some questions. So what are some applications IR spectrum? Yeah.
So you can use it for flower analysis.
Good. What's the difference between dispersive and FTI? You look like you want to answer. Go ahead.
I don't. Is that the types of methods where it's like red light is either being dispersed off of the sample or it's being absorbed into the sample?
Yep, and what this really tells you is that it's one light, one sample, one spectrum versus FTIR, which is you've got one sample, you've got one source of light. How many spectra per run? Yes, and you can actually pick how many you want. Usually I like to pick about 10,000. So, because if you run a sample 10,000 times, your signal to noise ratio is going to be a lot more awesome than if you do it with dispersive. Okay, so the type of energy that's absorbed. Bending, stretching, rotational, vibration. Those are the types of things. So. Okay, so mid-range IR for milk composition. Is it a primary method or a secondary method?
Secondary.
Yes. Yes, I am sure that's going to be an absolute. Okay, so Raman, vibrational spectrum, we talked that it's complementary to IR. We talked a little bit about Rayleigh scattering. That's where the scattered photon comes back to the same energy. Although some people do use Rayleigh scattering as an identification method, but those are like the people who are probably in the physics department. We don't need to think about that too much. But Raman scattering is when back down to ground level. There's some extra energy left, stuck. And that's what's going to scatter light. So we talked that it's a laser. Ooh, the other nice thing about Raman is that if you've got something with a lot of water and you can't filter out the frequencies that water is most IR active, because water is so IR active that it will swamp your signal sometimes. So clearly the milk analysis people have figured out how to avoid those frequencies that water or liquid just swamps out a signal. But if you can't do that, Raman is really great for that because water is not Raman active. So you can actually, if you've got like beer or a fruit drink or something like that, you could also use Raman spectroscopy to identify the sugars in it. It's not as easy to work with, quite frankly, because the math involved for quantifying an IR is a lot more straightforward because you never can quite guess when the electrons are going to come down to ground state or not. That actually puts a bit of uncertainty in your quantification for Raman spectroscopy. So what I did for my PhD is I used IR and Raman to quantify sucrose and to identify not only the percent sucrose in a system, but was it crystalline sucrose or amorphous glassy sucrose. So I was able to very straightforward, simple linear regression, do that in IR. But I needed to have a multiple linear regression in order to quantify in Raman, just because of that little uncertainty of not only the energies, but then also crystal morphology was kind of messing things up a little bit because it scatters light a little differently. And I burned some samples, obviously, as I had mentioned before. I actually tattooed a Cheerio with Raman, which was kind of fun. So I actually tattooed my initials in using a Raman laser. I was trying to measure the sugar content on a Honey Nut Cheerio, which I did. And actually, Amy Mortensen, who got her master's degree out of here, she was Pam's and my first master's student together. And so she used Raman and IR spectroscopy to quantify sugar on a Honey Nut Cheerio and map it, because she combined it with a microscope so that we could see where the sugar was. And, that way, if we wanted to reduce sugar, did we get the right coating? Did it have the right structure so that it refracted light properly? So it was a really cool project, but I just remember we toasted a few Cheerios with that one. So it was fun. Let's see. Diffuse reflectance. There's a lot of different ways. This was the one with the I think this is like the reflectance one, where I was saying like the incident light. And then so here's your incident light coming in, and then you've got crystal, and it can actually move the light. You've got your sample here, and how does it refract the light? So these are different ways, different spectral ways. It's still the same wavelengths, it's still the same lasers, but the way you position and handle those samples, you can start to see things a little differently. So like ATR or something like this might make it a little simpler for sample handling, as opposed to, again, if you want to put it in neutral, or if you want to put it in KBR, or if maybe you don't have the appropriate cuvettes, then you can start using things like this. One of the problems with these types of systems is sometimes, like with the ATR that I had used, I actually ended up contaminating the probe itself with corn syrup. And especially I used corn syrup that was 3060E, which is super viscous. And they actually couldn't get it off the detector probe. So they had to actually soak it in alcohol for a few days to try and get that cleaned up. But so sometimes, that's important, sample handling. The other thing that's important, two things that's important for IR, particle size. You must control particle size and shape, because if you're doing any kind of reflectance or refraction type stuff, the grind is really important because it's going to refract light in different ways. So make sure if your flower is ground to a certain particle size, it needs to stay consistent. The other thing that IR systems are sensitive to is temperature. So if you put an IR spectrometer, a probe in line, maybe it's fryer oil recirculation loop to make sure that your fryer oil is still of good quality. You need to make sure that that temperature is well controlled, because the higher the temperature, the bigger the signal that you're going to get, and the more chance of swamping, and that you won't be able to actually tell the difference between things. So those are the things you need to control. I think we are almost out of time, or are we out of time? Oh shoot, you guys need to tell me these things.
Okay.
Anyways, there you go. I was talking a little bit about near IR. Let me just say one more thing about near IR. Near IR can check overtones. So another thing is, if you've got a lot of water in something and it's swamping out your signal, go up to the near IR frequency and you should be able to see things. So again, it takes more energy because the wave intensity, the absorption intensity is not as high, but that's another way to avoid water swamping. Okay, now I'm done. I'm totally done. Thank you.